I'll just quickly introduce you. Yeah, so thanks for coming to give a talk. Chin, she was a former student at NYU, but even before that, when she was a undergrad at Tsinghua, she visited us, our lab during one summer, and remember working with her, and it was a real pleasure. So when she came back as a master's student, it was really great. She did her dissertation, thesis work, I guess, with Li Jin, Professor Li Jin, and then got her PhD studies with at Cornell, which I guess you're still finishing up right now, right? Yeah, the topic looks very interesting. So looking forward to hearing more about it. So yeah, please go ahead and welcome her to the talk.
Hi, everyone. Thanks, Joe, for your introduction, and thanks for inviting me to come back to give a talk. So during 2019 to 2021, while I was here, I have seen some familiar faces like Yu Tang, my previous colleague, and Jenny. And also some new faces here. I'm currently a fourth-year PhD student in operations research at Cornell. My name is Qian Xie. Today, I'm going to talk about a machine learning related problem called cost-aware and feedback-aware Bayesian optimization by applying some concept called Gittins indices from decision-making and economics problem. My talk would include two parts. The first part is about the cost-aware Bayesian optimization part, and the second part is about feedback-aware Bayesian optimization. So the first part, you can check out our publication at Neuropes 24. And the second part is still an ongoing work. And I'm also glad to discuss about the potential of this ongoing work with applications in transportation. So since I need to leave at about 3:40, so I want to keep my talk in 40 minutes, and then we'll stay here for about an hour chatting with students here. Okay, so I'll get started. So let me give you some motivation about Bayesian optimization. So Bayesian optimization is mainly for solving parameter optimization problems. Say, for example, in machine learning, we may want to do hyperparameter tuning. Because, for neural networks, there are like number of neural network layers, the width of neural network, learning rate, something like that. So to tune these training parameters to achieve high accuracy or low loss, Bayesian optimization can be a method, can be an efficient method. And also this animation is showing a lunar lander control problem, which is simulated in OpenAI interface. So, we want to, there are a lot of control variables. Say, for example, the angles, the speed, and then we want to achieve high rewards. So such reinforcement learning problems, such stochastic control problems, how to find the best set of control variables to achieve high rewards can also be studied using Bayesian optimization. The third application I want to talk about is adaptive experimentation, say for electronic commerce. We might want to design different websites, different user interfaces, or some other decision variables to achieve high revenues. So for these market decisions, you can also consider Bayesian optimization. So say, for example, Meta has an adaptive experimentation team applying Bayesian optimization to recommender system or A/B testing, for example. So since the audience here is working on transportation, I also found Professor Osby and say Jenny and you and other researchers here have also done a work studying how to find the market penetration rate to achieve high system performance, applying Bayesian optimization approach. So the context is connected vehicle deployment, and the system performance here involves two parts. One is the average time, and the other is average queue length. So we want to minimize both these two parts. From my perspective, this problem can also be studied, also be modeled as a multi-objective optimization, which has some related works, but still have potential to improve for this multi-objective optimization, because in multi-objective optimization, you might want to find the Pareto optimal frontier, and which might be a little bit trickier. Anyway, so the applications I mentioned before, they can be viewed as black box optimization, where you take some input parameters and you want to optimize some performance metric. Why they are called black box optimization? Because the objectives are typically non-analytical. They are somewhat complex to study. So say for that transportation example, you might run some simulation or some real-world deployment so that you can see the result. So it is not that analytical and without some gradient information to optimize. And often they are expensive to evaluate. So that's why I call black box function. So these black box functions are typically modeled as a function drawn from a stochastic process. And if you do grid search or random search, you might need a lot of number of evaluations. And I have mentioned that such function is expensive to evaluate. So we might want to have some smarter decisions. So that's how Bayesian optimization comes into play. So why it's called Bayesian? I guess you might have heard of Bayesian rule. So that is, you have some prior belief at the beginning, and then you apply some Bayes rule to update your posterior belief based on your data collected. So to allow these posterior updates, Bayesian optimization typically assumes the stochastic process to be a Gaussian process. because Gaussian distribution has many good properties to enable us to apply the Bayesian rule more easily. So here's an example. So for this one-dimensional function, we don't have much information about it at the beginning. So we assume the mean is 0 and the covariance is unit. And then say you have collected, say, for data here. And then now you can update your posterior belief. So you will see for the data you have collected, the mean is exactly the value of these points. And the variance also shrinks to 0 for these points. And then for other areas, if it's closer to these points observed, then you have higher confidence. For those regions that are further, you have a higher uncertainty. So that's basically a high level idea of how it works. Okay, then based on such posterior information, what to evaluate next? So now I have an exploitation trade-off. You might want to search the area where you have a higher mean, but somehow you also have higher uncertainty. Then how to leverage those trade-offs better to make decisions? Is there an optimal policy? So unfortunately, this problem typically has a continuous search domain. So I have mentioned in adaptive experimentation, you may have A/B testing. Basically, you have two versions. But actually, sometimes you are not determining between two versions. Sometimes you might want to find the threshold. And then say above this threshold, you might want to make this decision. And if it's below that threshold, you make another decision. So also for the connected vehicle deployment example, that market penetration rate can also be lying in a continuous search domain, which means that you have infinite number of possibilities. It's very hard to enumerate them one by one. And also, another property is that the values of these points can be correlated. So say, for example, for the market penetration rate example, you definitely would expect that the system performance of, say, two close market penetration rate values will be also close. So given these two properties, correlation and continuity, if we want to formulate a math language, it will give us an intractable Markov decision process. And therefore, the optimal policy remains unknown. Then how do people approach this problem? So I will first introduce a popular policy called expected improvement. This policy, I think, is also used in that market penetration rate paper because it's so popular and it's relatively easy to understand. So that is So first, consider the current best observed value, which is this point. And then now you have this posterior distribution given the data. Then, so we don't know this true objective function, but we can draw a lot of samples based on this distribution. And then you compare it against this current best observed value. If it is above, then you consider the difference. If it is below, then it is 0. And then such maximum of difference in 0, we call it improvement. Then we do an expectation over such improvement. So this is the idea of the expected improvement. So we can assign a value to each point in the search domain. And then we pick the point with the maximum expected improvement. So that's the idea of this popular policy. This policy is based on the idea of one-step approximation to that intractable Markov decision process. There are also other approaches that are based on other ideas. So say entropy-based approaches, they are based on maximizing, looking for the point with maximum entropy. There's also upper confidence bound, which is also consider a weighted combination of the mean and standard deviation. And also Thompson sampling, which is based on the idea of you draw a random sample from the posterior distribution and then maximize it. So each of these approaches based on some idea. And our work, Gittins index, is also inspired from another area. It also has its own design principle. So why do we propose another approach? So first, it's because it has competitive empirical performance. We have run experiments in both synthetic and empirical setups. So say, for example, we just consider the case if we know the prior, and then we draw samples from the prior. How will it look like? So we typically call such experiment to be Bayesian regret experiment. There are also some classical synthetic benchmark functions. For example, this Ackley function, which has a lot of local optimum. And then then you want to find the global optimum. So it's a good synthetic benchmark to test whether your policy will stop at one of the local optima. There are also some real-world benchmarks inspired from real-world problems. For example, the pest control problem and lunar lander problem. There are also some others which I didn't put in here. There is also a hyperparameter tuning problem and robot pushing problem. So here's our experiment result on those synthetic and empirical. The green curve is Gittins index, and these are baselines. These are including the most popular one, expected improvement, and also some other baselines I have mentioned, Thompson sampling, upper confidence bound, max value entropy search is one entropy-based approach. Knowledge gradient and multi-step EI, they are improvement-based approaches, and they are based on multi-step approximation to that intractable Markov decision process. And then in these experiments, you will find out that the Crane curve is consistently good. And the second best one can be some other. The second one is not always the same. So for example, you might find UCB are close to our policy in synthetic experiments, but they are not even the second best in these empirical experiments. There are also some other problems which our policy is not the best. So for example, the robot pushing problem, the robot pushing benchmark. But you know, somehow there's not always a policy that is consistently good in every case, but we always welcome a new approach that has competitive performance in most of the scenarios. Another reason for a new approach here is that Gittins index is also well suited for extensions to some richer variants, which incorporate some practical considerations. So in the following, I will talk about two variants. So the first one is cost-aware Bayesian optimization, which considers the case where we have varying evaluation costs. And the second is feedback-aware Bayesian optimization, which considers the case where we can observe partial feedback for every hyperparameter test. So for both variants, our Gittins index can be a new design principle. Okay. So now I'll introduce the first part. So I just mentioned three applications here where they all have varying evaluation costs. So say, for example, different number of layers of neural networks may have a different training time. And also for this lunar lander control experiment, you can see it can also have different landing time given different control configuration. And for A/B testing, for adaptive experimentation, different version might also need different advertisement costs or different human labor, different testing time. So in fact, almost every hyperparameter optimization problem can have varying evaluation costs. It's just the prior work may not have a very good idea of how to incorporate those varying evaluation costs. So they start from the standard setting. So in math language, besides this objective function f, we can consider another cost function. And then now the goal is to evaluate several points, not necessarily limited to a fixed number of t. So this t can be varied as long as the expected total cumulative cost is within the budget we have. So we call this expected budget constraint. So our approach starts from considering this property of cost-aware Bayesian optimization. And then to think about whether we can simplify it, whether we can convert it to another decision problem that has been studied. And the answer is yes. So we consider a discrete independent version of cost variation optimization. And this problem is called Pandora's box, which was not just first proposed by this Weissman's work, but also some other concurrent work, even though they are not phrased as the term Pandora's box, because sometimes they might call it Markovian bandit, but the idea is actually quite similar. I will later introduce what Pandora's box problem it is. But basically is that we have a set of Pandora's box at the beginning, and then you cannot see the value inside. You can only see the distribution of the box value inside at the beginning. And then open each box needs to pay a cost. And then you also want to find the box with maximum value inside within a certain number of steps. So here's the setup. Yeah. At the beginning, there are a set of closed boxes. We can see the distribution. We pay a cost and open a box and then see the value inside. And another box. And a third box. And then at some time, we decide to stop. And then we compare the values inside. We compare this fx1, fx2, fx3. And we see fx2 is the highest. And we pick the box. So our goal is to optimize the maximum of box value, subtracting the cumulative costs we have spent. Compare these two problems, you will find some similarity. Both are the scenarios where you can evaluate several samples, and both settings you want to find the maximum value. And both settings you need to pay some cost for evaluations. It's just besides this continuous discrete difference correlated independent, also this problem has a budget constraint, while Pandora's box problem has the cost explicitly in the objective, which we call a cost per sample setup. And the Pandora's box problem has an optimal policy, which is exactly Gittins index. The high-level idea of Gittins index is that based on this prior stochastic distribution and cost, you can assign a deterministic Gittins index based on it. If it is an open box, then Gittins index is exactly the value inside. And keep in mind, the higher is better if you want to do a maximization problem. And lower is better if you want to do a minimization problem. And then you open the box with highest index if it is a closed box. And select the box if that box with highest index is happen to be open. And in this case, you will stop. And our contribution is that we translate the Gittins index in Pandora's box problem to cost of variation optimization. So how do we convert? How do we translate? So the first is that we try to convert between cost per sample and expected budget constraint. And the idea is based on Lagrangian relaxation. So that is the Lagrangian multiplier we want to add before the cumulative cost here can also be viewed as a scaling factor. That is, if given these costs, they can be in dollars, they can be in Chinese yuan, they can be large, they can be small, they can be in the unit of time, they can be in the unit of price. But whatever, you can have a scaling factor added to it, which serves as the purpose of the Lagrangian multiplier of this budget constraint. And this scaling factor is also budget dependent. Okay, so basically, after scaling the costs, we again run the Gittins policy. And then the Gittins policy happens to be optimal for this budgeted Pandora's box. So now we have solved the issue, the conversion between expected budget constraint and cost per sample. The next question is, how do we go from discrete to continuous? How do we go from independence to the correlated case? So the idea is that we plug in the posterior distribution that I have previously mentioned to solve for the Gittins index. And now the Gittins index is also no longer a value for these discrete boxes, but for this setting, is a function. So for each point in the search domain, we can have a Gittins index value, and they together can be viewed as a Gittins index function. And then we also now the next point to evaluate is based on maximizing this Gittins index function. Yeah, so in summary, we consider scaling the cost and incorporating the posterior when we're trying to translate the Gittins index policy in Pandora's box to cost of variation optimization. I also want to talk a bit about the lambda, that is the scaling factor I just mentioned. What's the role of it? So basically, if you already know the cost conversion, then just go for it. Then just directly do the conversion. If you have a budget, then from the high level idea, if you have a larger budget, then you pick a smaller cost per sample, which can also be viewed as a higher exploration. So say, for example, this lambda is small, so it actually decays, the regret decays slower than the higher lambda. But you will see it would end up with a lower regret and lower performance. So from this plot, you can see, oh, if you have a small budget, about like 40 or 50, then you might want to pick a larger lambda like this. And then if you have a larger budget, say 150 to 200, then you might want a lower lambda. And also this lambda cannot be a constant. It can also be a decaying schedule. If you have not a good idea of how large your budget is, then that schedule can also be a choice. So compared to expected improvement, which has our Gittins index has an extra parameter to tune, that is this lambda. You might worry about like what this extra parameter is, but it can also provide you with more flexibility. Is Gittins index good for cost-aware Bayesian optimization? So previously, I have showed you our experiment results in these setups for only the uniform cost case. And then we have also tested in varying cost case. So for synthetic problems, we just pick a cost function, say the linear cost function to test. And then for these empirical problems, based on their setups, we know what the cost function is. So this cost function can either be known ahead or unknown ahead. So for both settings, our Gittins index can work. So say, for example, for this lunar lander problem, until the lunar lander lands, you know what is the landing time for it. So that can be viewed as an unknown cost case. But for both setups, our Gittins index can work well. Okay, the second part is observable partial feedback. So in those previous applications I have mentioned, say hyperparameter tuning, you can observe a training curve while you do the hyperparameter testing. And also for adaptive experimentation, you can also observe the profit curve, or the click-through rate curve, or the user engagement curve. So for these applications, how can we incorporate such partial feedback information to help us make better decisions? Okay, so here is the math setup. So now you can observe the performance curve, which can be modeled as fxt, where now you have an extra parameter, extra argument t here, representing the time. So that for each x, you can observe a curve in terms of time. And then you want to pick the best x that has the optimal final performance metric, which can be represented as this fx big Tx, where this big Tx represents the full evaluation time of hyperparameter x. That say, for example, in hyperparameter tuning, for this hyperparameter, you may run 100 epochs. For the other set of hyperparameter, you may run 200 epochs. And then after running this number of epochs, you will get a training loss or training accuracy. And then you want to find the best hyperparameter that achieves the highest accuracy. And you also want all of your total evaluation time should be within the certain budget. I just mentioned that we want to make smarter decisions given this property of partial feedback. That is, sometimes when we run this, when we observe this training curve, while we are here, and then we think it is not that promising, then we can actually pause here and then switch to another hyperparameter test. And then later, if we find this one is promising, and then we can resume back and then run until it finishes. So this pause and resume setup is called freeze-thaw Bayesian optimization, which has been studied by this prior work, where they proposed an entropy-based approach. And from our view, this entropy-based approach also lacks of a guidance to incorporate partial feedback. So we also hope to apply Gittins index to this setup, because Gittins index is inherently feedback aware. So why do I say this? Where does Gittins index come from for this context, for this setup? So again, so look at this freeze-thaw Bayesian optimization, which also has some hard properties. That is, besides spatially correlated, it is also continuous time. And again, we also want to try to convert it to some decision problem that has been studied. And in this case, it is the nested Pandora's box. So now, different from the previous case where we have a set of closed boxes to open. And now we have several baskets of nested boxes. And then each time you can open an outer box and then observe some signal that is relevant to the value in the innermost box. And then until you open the innermost box, you can pick this box and earn its value. So this setup, for this setup, Gittins index is also the an optimal policy. It's just its form is more complicated. So how to translate to freeze-thaw Bayesian optimization would also be trickier. And this is our ongoing work, and we hope we can finish it in a few months. And this ongoing work, we think it also has a lot of potentials. So far, the potentials we have seen can be in several applications. So the first is the hyperparameter tuning I have just mentioned, how to incorporate the training curve information during neural network training. There might also be some other information such as gradient norm during your training. And the second application is in some science experiments. So say, for example, in plasma physics, in those fusion experiments, they also they are also very time consuming, and you can also observe some stability curves during your science experiments. So that can also be an application. And the third application is Bayesian quadrature, where quadrature is like basically integrals of something, and then you test some points, and then you do the integral. And in those problems, there are also some hyperparameters to optimize. And then you can also observe some interim results of this quadrature. And I'm also happy to discuss with you whether there are some potential transportation applications for this setup. Yeah, so basically, in summary, we propose a new design principle, Gittins index, that we have studied for the problem of cost-aware Bayesian optimization with varying evaluation costs by linking to Pandora's box and Gittins index theory. It has competitive empirical performance. And right now we are considering extending it to free-solve Bayesian optimization for optimizing black box processes with observable partial feedback. And there's also some potential for not only free-solve Bayesian optimization, but also say multi-objective optimization I have just mentioned. It's just it's still unclear whether what would the Gittins index look like for multi-objective version of Pandora's box. So that is also an ongoing work. I also have an ongoing work about rather using the Gaussian process for updating the prior and posterior. We do not need to rely on those surrogate models to maintain our belief. Instead, we can use reinforcement learning to learn acquisition functions, including Gittins index acquisition function. And I'm also happy to discuss other potential directions with you. So I think I will stay here for around here for a while and happy to discuss with you. Thank you. Let me see if there are any questions, both here and online. Yes, please.
I have a question regarding your, it's a high-level question regarding your work. So recently, I heard some topics about the test time training. So that means the test time training is the kind of training model. During the test time, the distribution that we see are totally different from what we have seen in training. So I wonder, is there any potential can your work be applied to this type of scenario? Like, during testing, because we have limited data, basically this initial
Decision making.
Yeah, fine-tune their decision and tuning stuff.
Yeah.
I'm curious, is it possible like to see any connection between your work and the past practice?
Could you explain more about the distribution change in your context?
Oh, right. So, like, for example, like during training, we're planning a lot of data and we train a model. But when we want a model in the brand new scenario, have some specific data.
Yeah.
During training, but which basically is only different from what we can
see in
the training. And the idea of the test machine is that during the test time, as we see new data from the test environment, we kind of like trying to retrain the model as we see new data. Is there possibility to or are you trying to solve this task?
Oh, I see. I get it. So is it like some transfer learning, or say, for example, in LLM, you might want to consider some smaller number of parameters at the beginning, and then try to apply it to more hyperparameters. So say transfer learning can be like something like you first train for some computer vision task, and then like apply it to some other computer vision task, or some NLP, or some other things. But
yes, the similar thing is that during test time, the budget is also limited.
yeah,
So we don't want to test train on during testing forever. So I think that's kind of similar to what you can describe in your.
yeah, I think my case can be for the first part, but I'm not an expert about how to apply. So after, say, you train on this task, and then you apply it to some other tasks. So I guess so. I have talked about. Oh yeah. So here, so this synthetic experiment, I think, can be considered of the case where we know the prior, and then all the objective functions are also drawn from the prior. But in the reality, I think actually we don't know the prior. And then very similar to the scenario you described. So most of the time we might have a misspecified prior. So say, for example, what actually the prior should be good for this case, or we don't know. And then we start from just start from something called matter 5-half prior. And then we continue do our evaluations. So from my understanding of the scenarios you are describing, it's about the surrogate model misspecification. That's also a big area that people are working on. That is how you can model your belief better, and then how to update the prior and posterior better. Well, my work is mainly focused on the decision-making part, the acquisition function part. That is, once you have such posterior belief, how you pick the next point to evaluate. So I think the goal is slightly different here, where the surrogate model is also an important research topic within Bayesian optimization. And also the idea of one of my ongoing work using reinforcement learning to directly learn this Gittins index function, so that we do not need to bother with the surrogate model misspecification. Yeah, I think that's basically my understanding. Yeah, any other questions? Yeah, I'm happy to discuss more with you on this later. Are there any questions online or here?
No questions online.
Great. So if there are no more questions, so I'm happy to just walk around and then chat with anyone here. who is happy to discuss. Thank you.